Okay, welcome everyone to HEC Montréal's Chair of Energy Sector Management webinar series. Today we're going to be having a webinar on the cost benefits of different technologies for decarbonizing freight, and specifically looking at two case studies, one in Alberta and Germany. The reason for, launching this series, and we have actually quite a few on freight transportation, is because the sector, as most of you know, is quite complex and quite difficult to decarbonize, given its significant growth over the last 20 years and also its dependence on fossil fuel. So getting to zero emission in this sector is going to be quite a challenge, in large part due to the infrastructure and as well the cost. And so the interest of this webinar is basically to look at the results of two case studies, as I said, that's compared the cost and benefits of different technologies for decarbonizing freight on a life cycle basis. One, like I said, for Alberta, with a particular interest for hydrogen technology, and the other in Germany, which is looking at overhead electric catenary road systems as an option. So I'm Joanne Whitmore. I'm a senior researcher at the chair, and the two guests that we have today, one is Jessica Loft. She's a research lead on hydrogen and transportation for the Canadian Energy System Analysis Research Initiative at the University of Calgary. Her research work explores low carbon pathways for Canada's transportation system, has contributed to the launch of the Alberta Zero Emission Truck Electrification Collaboration Project, which includes the design, build, and road testing of two hydrogen fuel cell electric Class 8 trucks. Jessica has a decade of business experience in the railway and trucking sector, and she has a master's science degree in sustainable energy development, as well as a bachelor in commerce and finance. The second guest speaker is Moritz Moschal, who is a senior researcher in resources and transport at the ICOS Institute in Germany. He's been with the organization since 2009, and he's been involved in a series of long-term scenario analysis on energy efficiency and greenhouse gas emission reduction in the transport sector. His focus is on technical options for energy efficiency and alternative drive concept for heavy-duty vehicles, including the ERS, which with a special focus on overhead trucks. He has a degree in environmental engineers. So just before we start with the presentation, so you know, this event will take about an hour. Each presenter will have about 20 minutes for their presentation, and at the end we'll take about 20 minutes of question. And the way it's going to work is that if you look at the on the right hand side, there's a box that you can click on, which reads question, and so in there you can just type in the question, either specific to one of the presenters or something that is open to both of them, and I'll read them, and for the time remaining we'll take as many questions as we can up to 11:30. So with that, and just so you know, Jessica and Moritz, I'll read the question so you can just focus on answering. So with that said, I'm going to transfer the control to Jessica, and so she can start her presentation. And oops, there you go.
Okay, so I'll give this a go here. Is it all good? You can see my screen?
Yep.
Yes, good. Okay, well, my name is Jessica Loaf. As Joanne said, I am with the CSER initiative at the University of Calgary, and I'm also associated with the new not-for-profit organization, the Transition Accelerator. So Joanne from the HEC had kindly invited me to talk about our recent research series, which is called The Future of Freight, and it explores zero-emission diesel alternatives for road freight transportation in Alberta. So Joanne and HEC, thanks so much for inviting me, and thanks for all of you for attending this webinar. It's nice to be able to share the results of this study. So before I get into the details of this study, I want to provide some context of the work that we do at CSER and the Transition Accelerator. All of our work is really geared towards reaching Canada's climate change goals of being net zero by 2050. We see these targets as being massive, huge, and something that's not going to happen through in the margins or through incremental improvement. It is going, and that's especially true if we want to maintain our economic prosperity and still grow our population. So to achieve these goals, we're going to have to look for transformative systems level changes. So we have to look to build compelling and credible transition pathways to get from where we are today to where we need to be in 2050. So these pathways will include a series and sequence of technological, business model, and social innovations, and many of them being disruptive in nature. And these innovations must be configured in ways that can get us to reach our greenhouse gas emission reduction targets, but they can also be made more compelling by addressing other issues that are inherent in these systems. So the general approach that we take is we first work to understand these systems, the systems that we're dealing with. We really want to understand the forces that are driving change. And so we model and analyze these changes, and we do this while engaging directly with key stakeholders. You know, it's really an iterative process. And it is the approach that we took for this Future of Freight series. But ultimately, what we want to do is we want to co-create a shared vision with the key players and bring together a consortium of companies that can actually drive this pathway forward. So here are the 3 Future of Freight reports that we conducted recently. So in Report A, we look to understand Alberta's road freight sector. In Report B, we do a techno-economic environmental assessment of 4 zero-emission alternatives for trucking in Alberta. And in Report C, we look at the impacts to the energy system that this transition pathway will have. So we'll start with Report A. Report A is really a fantastic report that documents the current state of freight transportation in the province, and along with looking at all the historical and emerging trends that are going on. And unfortunately, I don't have time today in today's session to give a detailed overview, so I'm just going to give you the key learning. So this sector, it's a large contributor of greenhouse gas emissions, accounting for about 8% of the province's total. But it is also challenged with many other issues, from air pollution to inefficient load management to labor shortage to low profit margins. You know, all of this really makes the sector poised for disruption. It makes it a hotspot for innovation. And when we spoke a lot with industry, and what we heard from them is that they're really ready to embrace change. This took us a bit by surprise because we were expected them to be reluctant, but they weren't. They were ready to embrace change, and it's because of all these issues. And they really wanted to be the drivers of their own destiny. They wanted to be a part of this pathway. And really, this attitude makes it an ideal place to start and embark on this transition pathway. So quickly moving on to Report B, and this is the techno-economic assessment for the zero-emission alternatives. In this report, we start with the current technology, and this technology dominates the freight sector all across North America, and likely across the world as well. And it is the diesel internal combustion Class 8 truck. So in our study, we took what we saw was a typical shipment, in the Alberta landscape, and it is a 27-ton truck, and that includes 17 tons of payload. And it traveling a distance of 700 kilometers in between refueling. And what we wanted to do is we wanted to understand the energy flows of the system. And to do that, we used a Sankey diagram, like the one you see here. So the way you read this diagram is you start with the primary energy on the left-hand side. And with each process along the value chain, you track the losses until you get to the end, which is your kinetic energy, which is moving the wheels. So effectively, it's a well-to-wheel analysis. However, when we were conducting this analysis, we actually start on the right-hand side. We assumed that we took a typical diesel truck, and we assumed a fuel efficiency of 38 liters per 100 kilometers. And we assumed a drivetrain efficiency of 35%. And what this means is for every liter or joule of fuel energy that is consumed, 35% of it is used to move the wheels, and the other 65 is lost as heat, right? So, and using a higher heating value, we were able to determine that the kinetic energy demand for this typical shipment is 3.8 gigajoules per truck. So this is an important number. And so we use this number, as all else being equal, for the alternative drivetrains as the basis of analysis. So what's important to note about the diesel system is that it is very mature, and it's evolved through continuous improvements over many, many decades. So with laws of diminishing returns, future improvements of the systems are likely going to be small and likely expensive. You'll see there that the majority of the losses are at the powertrain, at the drivetrain. And there is a lot of work. There's a lot of work being done to improve the efficiency of the drivetrain. However, these improvements are likely going to be very incremental and not going to get us to that transformative system level change that we're looking for. So let's see how the other systems compare. So let's start with a biodiesel system. So we looked at a bio-based system, and we look at to that same 3.8 gigajoules of energy per trip, gigajoules of kinetic energy, I should say. But we are starting with a biomass that is converted to a liquid fuel using a Fischer-Tropsch technology. We'll see here that you'll still have those significant losses at the drivetrain, but you're also going to have significant losses with the refining process. And what this makes is it makes a system that is 16% efficient on a well-to-wheel basis compared to the fossil diesel system, which has an efficiency on a well-to-wheel basis of 26%. Next, we considered a battery electric truck. The battery electric truck has an electric motor, which is very efficient. But it will see some other losses with the charging and electronics. And another area of loss will be with the power production. And you know, this is an area that is commonly overlooked, but it must be accounted for on a well-to-wheel basis. So in Alberta, we considered a future grid. We considered a grid that is 30% renewables and 70% natural gas combined cycle for this analysis. So this provided us with efficiency of 34% on a well-to-wheel basis. So the hydrogen fuel cell electric, it will also provide, or it also has an electric motor, which gives us the same efficiency gains on the drivetrain. However, because of the fuel cell, which converts hydrogen, which is stored on board, into electricity, there's an extra step in the drivetrain. So there's an extra source of loss that needs to be accounted for. And then, of course, the hydrogen needs to be produced. So in this scenario here, we're looking at a blue hydrogen scenario where we're converting natural gas into hydrogen using a steam methane reform technology. And so we'll have some losses there. And then, of course, there's distribution. So if we're looking at a green hydrogen scenario where we're taking wind and solar power generation to provide the hydrogen or produce the hydrogen, it'll be a similar drivetrain system, but we'll see losses with the electrolysis upstream, which is used to produce or convert the renewable power into hydrogen. So both the hydrogen systems have and the battery electric systems have a higher efficiency than the diesel system already. But why do we care? Why do we care about well fuel efficiencies? Firstly, in a sustainable future, the less resources that we consume, the better. It just makes sense. You want to use less resources. But it also impacts the cost of the energy and the greenhouse gas emissions, which is what we're going to look at next. So by following the energy flows that was presented in the Sankey's, we were able to estimate and compare the cost of the kinetic energy to move that typical system. So that's that 3.8 gigajoules. So by using this method, we are able to compare each of the systems equally while taking into account the differences in efficiencies. So we know that for an alternative technology to be credible and compelling, it needs to be competitive with that very mature diesel system. We see that bio-based diesel costs are the most expensive or the most costly, where battery electric is the least costly. So that's that there. For the hydrogen side, and actually even the battery electric side, we see that the cost of distribution is a major source of cost. And it's an area of great uncertainty, and that drives the cost really high. And the reason for that is because the distribution systems, for the most part, are non-existent. However, with scale, we project that these costs will come down substantially. If we look just at this blue hydrogen option, so hydrogen that is produced through natural gas with carbon capture and sequestration, we see that the wholesale cost of hydrogen, so at the top of the red line or the orange line there, it is actually about half the price of the wholesale price of diesel. And in fact, Alberta is globally known as one of the lowest cost producers of blue hydrogen in the world. And this includes the cost of CCS, so carbon capture and sequestration. The green hydrogen is more expensive than diesel, even without accounting for the distribution. So if we use the opportunity to use the cost advantages of blue hydrogen to help build up that necessary infrastructure, this would complement the green hydrogen production and reduce the cost for both and make them both more competitive and likely very comparable to the existing diesel cost in the diesel system. Next, we move on to greenhouse gas emissions. So when we compare that typical trip against the diesel baseline, we find out that with Alberta's current grid intensity, the battery electric option is actually has a greater carbon footprint than the diesel system. But if Alberta is to adopt a grid that has 30% renewables with 70% natural gas combined cycle, emissions would be reduced by 50%. That's substantial. For the hydrogen fuel cell electric systems, what we're doing here is we're effectively shifting the emissions from a tailpipe, and this is a place where it's very difficult or impossible to manage the emissions. We're shifting them to a place upstream where they can be managed through carbon capture and sequestration. So in the natural gas production, even without CCS, we can achieve a 25% reduction. But we have the resources and capabilities to use CCS. So with CCS, we are able to reduce emissions by 71 to 81%, depending on the grid intensity for the electrical requirements needed for compression activities. So the last one I want to point out is the bio-based diesel option. Bio-based diesel option, and I'm not going to get too much into this. The bio-based diesel is often thought to be net zero, but studies have suggested that that is not actually the case. It's going to depend on how the biomass is extracted, but also the decomposition rate of the biomass itself. And one of my colleagues at CSER, and this is something that they study and analyze exclusively. It's a very interesting area of study. So beyond the cost and the carbon footprint, for the zero emission pathway to be compelling, the technology must be able to perform its intended duties as well or better than the incumbent diesel option. And there are many measures where the industry may not be willing to compromise depending on the duty cycle. So all the factors here are important. They're important to the end users. The electric options, whether it's battery electric or hydrogen fuel cell electric, they're very appealing to the industry that is challenged to secure a labor force. And you know, it has a power and torque and drivability advantages that outperforms the diesel option. It should also have lower maintenance costs, which provides reliability and operating cost benefits. But where the two technologies, the battery electric and the hydrogen fuel cell electric differ, it's with the range and the weight. Because of the heavy battery weights and the lengthy recharge times, the battery electric may not be suitable for long haul, heavy shipments, where the hydrogen fuel cell electric vehicle should perform well. And this is a duty cycle that is very common in Alberta. So the work that CSER conducted in Future Freight A and B and our stakeholder engagement process actually has led to what we call the ACE-TEC project. It is known as it stands for the Alberta Zero Emission Truck Electrification Collaboration. What this project involves, it involves the design and build and testing of two Class 8 hydrogen fuel cell electric trucks. And these trucks are being designed for a typical service on Alberta highways. So these trucks have a gross vehicle weight of 63.5 tons. And this is what the industry communicated to us is this is what they need. This is where they want to see this truck perform. So a 63.5 ton truck is this B-train configuration. So two long trailers being pulled by a single truck. This truck is going to be tested in between Edmonton and Calgary on a round trip basis, and it should be able to have a range of at least 700 kilometers in between fueling. Currently, the truck is in the design phase. It's being engineered right now, and it is expected to be completed. The build of the truck is expected to be completed in fall of 2021 and be road tested in revenue service by Bison and Trizen, two large companies that are often on the roads in Alberta. It'll be tested for an 18-month period. The hydrogen being used for this demonstration project is going to be pulled from the steam methane reforms production facilities that are already in Edmonton. And unfortunately, we're not able to include carbon management for this pilot, and it's just a result of the small size of the project. We are going to be using a mobile refueling system at a location in South Edmonton. The other thing I want to say is this project is being led by the Alberta Motor Transport Association, who represents all the carriers, commercial carriers in the province. And this is important because it indicates that the industry wants this change and they want to be driving it and want to be included in the process. And it is effectively a technology pull rather than a technology being pushed on to them, which is what they wanted. So it's not going to happen with one stakeholder. We wanted to look for a consortium of companies to come together, and this is all the partners that are involved in the ACE-TEC project right now. So moving on to our final report, there's Future Freight C, where we're looking at the energy impacts. And so what do I mean by this? So as many of you probably know, we in Alberta think of ourselves as being in the oil business. We are proud of the fact that we love the oil and gas industry, and for good reason. It supports our economy, right? So when we look at this, our primary industry here, we're pulling crude oil out of the ground. And that crude oil goes to refineries across North America, all across North America. And it gets refined into various different refined products. 77% of those products are transportation fuels. And those products are consumed by Alberta, but they're actually consumed by a market that's 9 times the size of Alberta. So effectively, we are in the transportation fuel business. So in a net zero future, is there going to be a demand for this product? Right? And so when we look at the various uses of the demand, of the diesel demand, we see that the heavy duty vehicle sector is a key customer, right? So we should be very concerned what is happening in this industry. So in a net zero future, is there an opportunity for Alberta to still be a producer, supplier, exporter of a zero emission fuel? Is there an option there? So that is what we wanted to compare. Is there still that economic opportunity for Alberta to remain a producer, consumer, exporter to the same degree that we do right now with our oil product? So when we look at our bio-based diesel option, we looked at a second generation bio-based option. So that's a lignocellulosic option. So basically residual waste, straw, wood, that kind of thing. So we did an inventory of all the lignocellulosic resources that we have in the province, and we take into account, of course, the conversion losses from the Sankey diagrams that we saw earlier. And we can see that we do have enough resources to supply this market, the heavy duty vehicle market in the province. But if we wanted to meet the demand for all of the diesel that is consumed in the province, we have insufficient resources. And we are far from being in a position to be able to supply this fuel to an export market. So then we want to look at our capability to produce grid power to support the heavy duty vehicle sector and also to replace diesel in the other sectors as well. It may be possible. So to supply our freight market, we have to increase our grid by 25%. So our grid load would increase by 25%. To replace all of diesel, it would increase by 66%. But that actually means that we'd have to double the growth rate of our grid capacity by 2050. Double it, the annual rate by 2050. And that's quite substantial. When we look to the export market, you know, the increase in our grid capacity would be very significant. And realistically, Alberta doesn't really have a strong competitive advantage as a producer and supplier of low carbon, low cost electricity. So we're not in a great position to become an exporter and supplier of low carbon electricity. So when we look to the hydrogen options, we have to really quantify the amount of hydrogen demand that there would be. So when we look at the potential demand for hydrogen of Alberta's freight sector, we see that we are going to need 76 petajoules of hydrogen per year, and that's equal to 1.4 megatons of hydrogen per year. As I mentioned before, briefly, Alberta is already a producer of hydrogen, and we produce this hydrogen, well, to crack diesel and support the fertilizer industry. So this level, this 1.4 megatons of hydrogen per year, is actually about 55% of Alberta's current production of hydrogen. So it's something that is achievable. And if we're going to put an economic value to it, this 1.4 megatons of hydrogen, it works to about $7 billion for the province. So if we are going to supply North America with this zero emission fuel or very low emission fuel, the demand for that would be 13 megatons of hydrogen per year. And if we use that same logic, 13 megatons times a price of $5 per kilogram, that's an economic value of $65 billion. So this is of interest to the province. So when we look at the resource potential, Alberta is very rich in natural gas resources. So if we just look at existing production, and combine it with the additional demand from the hydrogen market, we can see that we can easily supply not only our demand for hydrogen, but supply an export market as well. Next, when we look at green hydrogen and our capability and resources to support a green hydrogen economy, we have to think that as Alberta has a really high greenhouse gas intensity grid, when we think about green hydrogen, we would want to complement it with a transition to a low carbon grid with the introduction of wind and solar power generation, or increase in the grid mix of wind and solar into the public grid. So this is kind of a complex diagram, and I apologize for that but I think it's very, very interesting if we look at it. The CESAR team, when we were contemplating this, we developed a grid model, and this is essentially the output of this grid model as we look to increase the percentage, the proportion of renewables in our grid. So if we look here on this side here, this is the grid composition that we have today, roughly. If we're going to go to that 30% target of renewables by 2030, which was the target of our previous government, and hopefully the current government continues on with that, we'll be here. So this is the portion of renewables. But if we continue to increase the renewable capacity in our grid, but also supply the hydrogen market, we are going to be increasing the overbuilding the amount of wind and solar that is a part of our grid, but we're also going to be meeting the demand of our freight sector. So if we increase the grid size by 150%, and the wind and solar portion of it is about 115% of the current state is wind and solar, then we'll be able to meet this demand. To meet all of Alberta's diesel demand, we'll increase it a little more. But what's nice to see about this is the grid intensity of our public grid is dropping. Oh, sorry. That's my boss there. It is dropping substantially there. So when we look at this similar column charts here in terms of increasing the grid size, and it's following that same model there. To meet the demand for the freight sector, we have to increase the grid size by 150%, and that would include 3,700 4.8 megawatt turbines. So to support all the demand for diesel, the grid would grow by 205%, and that would be about 6,300 new wind turbines. And if we were to supply a market that is 9 times the size of Alberta, so the same as our current diesel market, we would have to increase our grid load by about 11 times. So that's quite large. And then we want to look at actually what is reasonable. Is what I'm suggesting on the previous slide which of that is reasonable. And we look at the amount of land that is going to take up to supply, to produce that level of electricity using renewables. So on the top row here, this is the footprint of the wind requirement for that transition. And on the bottom is the solar footprint. This is technically possible. It is compared to the size of Calgary. So it's technically a province, possible for our large province, but is it reasonable? Is it socially reasonable? You know, something to be considered. So I'm just about to end it here. Somebody once told me that in any presentation, you can only have 4 key messages or you will lose your audience. So I pulled up 4 key messages for all of you, and I'll just read them off for you. I want to say here that the heavy duty vehicle transportation sector, it does have high greenhouse gas emissions, and it is difficult to decarbonize, or has thought to be so. But from our findings, that the sector is really poised and ready for change. Secondly, the battery electric, both battery electric and the hydrogen fuel cell electric, they are appealing zero emission options, but it really depends on the end use duty cycle and the grid intensity. Next, the hydrogen provides an opportunity for Alberta to remain a supplier of transportation fuels in a net zero future. And this is really important. For a transition pathway to be compelling, it has to have economic value and be, you know, supported by the government and by investors, and this provides an opportunity. And lastly, I want to say that both blue and green hydrogen can be a part of this pathway. Like I said before, blue hydrogen has economic advantages. It is a low-cost option, and it can it can provide an opportunity to build up the necessary infrastructure and pave the way for ultimately the zero-emission green hydrogen to take shape. So I will end it there. I think there'll be questions later on, and I'll pass it off to Joanne and Marit.
Thanks, Jessica. We're a little tight on time. Hopefully, we'll still be able to take some questions. There's actually quite a few that came in. So I'm going to give the control to Marit. So Marit, sorry about that.
Yes, can you?
Okay. So you have control of the screen. You can go ahead.
So can you see my presentation in full screen, or?
Yeah, full screen. Thank you.
Okay, perfect. So yeah, thank you, Joanne. My name is Moritz Motschall. I'm from the German Öko-Institut. I'm happy to present some results of our work. I'm a senior researcher and in the transport and resource and transport division, and you probably don't know the Öko-Institut, so this is very brief, a commercial blog for us. The institute was founded about 40 years ago, and we are one of the largest independent research institutes within Germany, and our clients mostly are the European Union, national and state level ministries, but also companies, foundations, and NGOs. We have about 170 employees, and of which are 120 researchers. So part of our work since several years are alternative drivetrains and fuel options for heavy-duty vehicles. And today I want to share some results with you regarding the comparison of the total cost of ownership, so the TCO for different technology options. So these are the costs from a user perspective for Germany. So all of my slides are case studies for Germany, and might vary when it comes to the conditions in Canada. So the second part will be, I will show you costs for the whole transition, for the transition to a fully decarbonized long-haul freight in Germany from a macroeconomic perspective. So the TCO perspective is helpful when it comes to identify barriers for the users, to identify the influence of specific framework conditions. And the macroeconomic perspective is helpful to see which option is well suited for the whole transition. So let's have a short look why long-haul freight in particular is so important. In Europe, light and heavy-duty vehicles are responsible for about 35% of the transport greenhouse gas emissions, and these vehicles for long haul, I was very impressed, Jessica, from your 67-ton truck. So the largest truck we have is about 40 tons, I think. So these heavy trucks, they have high mileage and really high fuel consumption, so that they have a large influence on the total greenhouse gas emissions. And on the other hand, for these trucks, from today's perspective, it is very challenging to reduce the greenhouse gas emissions. So it's specific challenging because in Europe and in Germany as well, while the other sectors like energy sector, industry, were already able to reduce greenhouse gas emissions significantly, the emissions in the transport sector are still on the rise. So, and secondly, the projections shows that there will be the transport demand in Europe and Germany will increase within the next years. So the pressure to reduce these emissions is very high. So also that's why on the European level, there's already some measures to reduce these emissions. For example, there's a target of a reduction of 15% for a truck and until 2025, and a reduction of 30% until 2030. So within the next years, the consumption, the emissions should be reduced by 30%. So it's very challenging. On the other hand, we see for the regional and urban delivery freight, there is already a very well-suited solution on the rise with battery electric trucks. But for long-haul freight trucks, until today, there's no clear favorite yet. In Europe, the situation might differ a little bit from Canada because we have a lot of small countries. So it is highly important for the long-haul freight that we find a cross-border solution, so that only island solutions won't work here. So and the solution in the end must enable zero emissions on the road freight. So the European goal as well is for 2050, or the German goal is zero emissions for 2050. And these zero emissions should be reached with the lowest possible economic cost. So what are the options I will present you? We have the option is the direct use of electricity, for example, in battery electric trucks with very large batteries, which are very costly and maybe also have a very high weight, so there might be payload loss for these vehicles. Or you could use electricity directly in overhead catenary electric vehicles. So this is basically, you may know it from the train system. You have an overhead catenary system, and the truck charges the battery or gets the energy directly from the overhead catenary while it's on the road. And it's possible to combine this technology with as a hybrid powertrain with a small diesel engine or a small battery to be able to run on sections without an overhead catenary system. The second, in Germany, we don't talk so much about blue hydrogen or gray hydrogen, because in our perspective, it's not a suitable option for a zero emission transport system because of the leakage and so on. So I will focus on the indirect use of electricity as other options. This is a fuel cell electric truck run with green hydrogen. So basically hydrogen produced via electrolysis from renewable electricity. And the last option is the option we have a combustion. We have a conventional vehicle with a diesel engine, and we use diesel-like fuel, which are produced from renewable electricity. So we call it power to liquid fuels or e-fuels. So yeah, these are the options. Let's have a look at the cost from a user perspective, the TCO. When it comes to TCO, it's very important to highlight that these include taxes and truck toll and energy prices. So this TCO is always very country specific. So these results might differ a lot in Canada. But for Germany, we have yeah, these are our results, and it is also important to highlight that there are, of course, a lot of assumptions. Here we have the TCO for a vehicle purchased in 2025 and 2030, and so there are a lot of assumptions regarding the cost regression of specific components of the vehicles, like fuel cell, like battery and hydrogen storage. And basically what you see, we have here diesel, fuel cell, overhead catenary, hybrid electric vehicles, so with a little diesel engine. Here overhead catenary battery electric vehicle with an electric driving range of 100 kilometers. And here's a battery electric vehicle with a range of 800 kilometers. And what we see is basically that the lower operational costs for these trucks with direct use of electricity, they compensate the higher capital costs already in the next years. But one aspect right now is missing, and this is the cost. These are the costs for the infrastructure, for the overhead catenary infrastructure, as well as the charging infrastructure and the hydrogen fueling stations. So when I add this cost here with 100% utilization of the infrastructure, but it's unlikely to have this high utilization in the market ramp-up phase. So I add 50% utilization of capacity, and you clearly see when the first users need to carry the full costs of the infrastructure, this is a huge market barrier for the introduction of this technology. Yeah, but the costs are only one aspect one difference between these technology options. Let's have a look at the energy efficiency, because this determines the demand of additional renewable electricity production in Germany. So here's the Sankey diagram as well. So you see a diesel truck with synthetic fuel, so power to liquid fuel, a fuel cell truck with green hydrogen, and an electric truck run with overhead catenary system or battery electric truck. And what you can see, so our starting point is renewable electricity generation. So we achieve overall efficiencies of between 20% for the diesel with power to liquid fuel, 30% with the green hydrogen, which is quite similar to Jessica's result. And for the direct use of electricity, we achieve efficiency of over 70%. So it is clear from a German perspective, at least, that we won't have the possibility to produce such amounts of additional renewable electricity. So for comparison, today in Germany, the share of renewable electricity is about 46 to 50% in the mix. And in 2017, it was 210 terawatt hours. So it would mean that if we use green hydrogen produced in Germany, the whole electricity from what we have today almost would be necessary for long-haul freight and fuel cell electric vehicles. So so from an energy standpoint, it's like from a German perspective, is direct use of electricity will be possible to produce electricity within Germany for fuel cell or for power to liquid. It is very likely that we will be dependent on imports of these fuels. So let's have a look at the macroeconomic perspective. what you see in this picture is the total cost for the transition from today until 2050 to a full decarbonized transport system for the long-haul freight in this slide, in this picture. So these are the additional costs compared to a fossil fuel scenario. We have three energy scenarios. In blue, this is the power to liquid scenario. Here in green is direct use of electricity in overhead catenary trucks with a share of 40% power to liquid fuels because they are hybrid vehicles, and with fuel cell, with green hydrogen fuel cell electric vehicles. So we have the energy, the cost for the energy supply and the distribution, the cost for infrastructure, additional cost for vehicles, and here the total cost. And what you can see is that at first, yes, the decarbonization of long-haul road freight is quite expensive, so there will be significant costs for this transition. But the lowest costs are on this scenario with an overhead catenary truck, so the direct use of electricity. In this scenario analysis, we didn't calculate battery electric vehicle. It's very likely that their cost will be in the long term even lower than the cost of the overhead catenary system with overhead catenary system with a hybrid, with a power to liquid fueled hybrid engine. So, but we have prepared an sensitivity. So because you can see here the energy infrastructure costs for hydrogen is very high in the scenario analysis. These are the assumptions we made. So what we have only like a core network of fueling stations, and lower cost would reduce the infrastructure cost for fuel cell electric, for the fuel cell scenario. And I don't know if you are familiar with the with the Berlin airport. In Germany, we have sometimes problem with the infrastructure development. So what is when we have higher costs for the installation of the overhead catenary network. So this shows us in total still the direct use of electricity is, from a macroeconomic standpoint, the best option, or the less costly option for the transition into a zero emission freight in 2050. And the results are very robust regarding this direct use of electricity. I want to highlight one aspect, because I don't know, in Germany we talk a lot about the cost for the infrastructure. These are the main topic we discuss when it comes to overhead catenary systems. But we see in this picture clearly that the total costs are highly determined by the cost of the energy supply. So infrastructure costs seems to be manageable. But as you have seen in the beginning, in the TCO calculations, it might hinder the market introduction if the first users need to carry these costs. So what is the situation in Germany right now? Currently, there are 3 pilot projects on public roads of these overhead catenary systems. Each has a length about 5 kilometers, so it's only a small segment, only to test and to show that this technology works. And when in our scenario analysis, we always, almost always, assume that the core network of 4,000 kilometers should be electrified. That then a huge share of the transport demands can be carried out with this on this grid. And I just want to make a brief comparison, because between the costs here, the investment costs for overhead catenary network of 4,000 kilometers for Germany in total would be more or less 12 billion euro. And for comparison, here the truck toll revenues, or the total investment costs for the infrastructure until 2030 is about 100 billion euro. For the broadband, it's also 100. And Germany has such a high share of renewable electricity today because of a funding scheme since the 2000s, and with this funding scheme, there was already funding for renewable plants of about 270 billion euros. So in this comparison, this 12 billion seems manageable. What we also did in our scenario analysis, we modeled different. We varied different aspects of our assumptions. So in the blue scenario here, what you see is the reduction from today, from the total greenhouse gas, from today's emission to the future's emission. So you have your million tons of greenhouse gases. And here's the reduction which is achieved in different scenarios. The blue scenario is a scenario where we have no exception for the truck toll for overhead catenary trucks. In the green scenario, we have a CO2-based truck toll with a CO2 price of 200 euro per ton CO2. And then we have the red scenario, which is basically a CO2 price of 80 euro per ton, but with an increased network expansion. So what we see is that it is very important so that the rapid infrastructure development is the key requirement for relevant greenhouse gas emissions, and that such framework conditions and tools like the CO2-based truck toll is very efficient to achieve this greenhouse gas reduction. So what are our main conclusions? I think I have 5 points. I'm sorry about that, but we know that we have seen that electrification enables climate-neutral long-haul road freight transport in the near and distant future, and that electric trucks can be run already in the near term economically if they don't need to carry the cost for the infrastructure. The direct use of electricity I have shown is the most efficient option, and it requires the least expansion of renewable energies of all these options. The infrastructure costs I have shown are particularly relevant in the startup phase, but in the long term of secondary importance. And the greenhouse gas mitigation is highly dependent on the speed of the infrastructure development. So what are the necessary next steps? What should happen to realize these greenhouse gas potentials? It is necessary to align freight transport policies with greenhouse gas emissions to obtain planning security for all market petitions. It is important to develop a reliable infrastructure expansion plan, and also the public funding of the infrastructure as a guarantee for the infrastructure expansion for all these actors, for all these stakeholders. It is also helpful to set minimum quota for new electric truck registrations, or to create more ambitious CO2 targets for heavy-duty vehicles after 2030, and to create framework conditions like a CO2-based truck toll which support the shift to zero-emission vehicles. And in the near term, it would be helpful to realize a larger scale implementations of these projects on public road space to gain more practical experiences. And as I said, for Germany or for Europe, important this international cooperation. It's important to create cross-border technology development and standardization from today on, actually. So, but what is our starting point? Where are we today? So there's a target in Germany from the German government for the year 2030. The target is that 1/3 of our road freight transport performance should be based on electricity in the year 2030. This is very ambitious. And what is our starting point? So in the end of 2019, we had the impressive number of 8 electric trucks in Germany with a weight of above 12 ton payload. So that's basically my presentation. If you are interested in our work, you can go to our website öko.com. You find all of our reports with detailed information and more. Yes, I thank you for your attention, and yeah, looking forward for your questions, and would pass on to Joanne.
Okay, thank you so much, Moritz. We're actually already pretty much at the maximum time, but I will take a few questions. So for those that have a little bit flexibility, you can stay on, and we'll take the questions for the next few minutes. So I'll just go a little bit with the first questions that came, which I think are more directed to Jessica. But basically, someone asked, have you calculated the carbon emission by truck trips for the different systems?
Yes, we have. So we took a comparable approach to assess the emissions on a per trip basis, but on a well-to-wheel scope. So that was part of our study for sure.
Somebody asked, what would a scenario for natural gas and RNG ICE would look like? Was it part of your study?
No, we did not include RNG in our study, and we had to draw some boundaries, and through our discussions with the stakeholders, you know, they felt scarred from their experiences with natural gas in internal combustion engines. So to us, it wasn't I guess a compelling option to look at.
On the GHG emission comparison figure, what means 0.1, 0.2, 0.3 under the bar? That's pretty specific.
Yes. So sorry if I didn't explain that well. So that is the global warming potential. So it's often thought that biodiesel is net zero, but through study and literature review, there's researchers that suggest that it is not, and that's because of the fuels that are consumed to extract the biomass, but also it depends on the decomposition rate of the biomass itself and the length of time it takes for the biomass to get to the atmosphere.
Why is the scenario with 100% renewable electricity for HFCE, but not for BE? It takes more electricity for HFCE than for BE.
Right. So yeah, I'm trying to remember what is included in there. Why is the 100% renewables for the wind and solar? Yeah, so we were looking at for that future grid where you're going to have 100% renewables supporting the hydrogen fuel cell electric system, the freight system, and we assumed that would be 100% efficiency there. We're envisioning that if we are going to adopt a green hydrogen system, then that would be integrated in conjunction with the increase of renewables into the public grid.
Can you please give more details on how is going to be measured the fuel consumption at the Aztec project? Yeah,
so for the Aztec project, we'll be analyzing and following the greenhouse gas emissions and the fuel consumption, and we'll compare it to a comparable diesel as the baseline. So it'll be the same model year truck to follow, and following that's operating on the same lane, so the same route. We can be comparing that against the two Aztec trucks and how much hydrogen they are consuming, and then we'll be we'll be calculating it on a life cycle basis as well. So we'll be tracking where the hydrogen comes from, so which hydrogen production facility, and calculating the carbon intensity of that greenhouse gas, the carbon intensity of that hydrogen production at that hydrogen facility.
Sorry, there's a lot of questions for you, Jessica, but there will be for Maurice. Is full natural gas life cycle included the exploitation and the distribution loss, as well as the leaking abandoned well in the GHG emissions?
Yes. Yes.
So yes for Jessica, and you can go ahead, Maurice, if you want to.
No, actually, as I said, in our calculations, we didn't look at methane-based hydrogen, yeah. Yeah, that's it.
That's pretty straightforward. But for Jessica, the answer is yes.
Yes. Yes.
Okay. I guess this is perhaps a last question, more specifically directed to you, Jessica. Do your models assume that CCS system will be 100% effective at sequestering carbon? Like, does it also take into account that there might be, fugitive emissions, or maybe
not? No. We assume that the carbon capture rate would be 90%, but we didn't account for any fugitive emissions or losses from after its post-sequestration.
Okay. So we have 3 questions left. We're doing pretty good time. Do you believe it is possible to combine the 2 technological solutions? A truck running, I think this is for Moritz, to have a truck running on hydrogen that has the possibility to link on overhead lines. This would make it possible to run on hydrogen instead of diesel when there's no overhead infrastructure.
Yes. Yes, for sure. This is an option for the technology, but you have to keep in mind that these new technologies are rated to high cost, and that it's possible, but from our perspective, it's much more likely that we have a combination between overhead catenary truck with a battery on board with an electric range of approximately 300 kilometers or so. So this is what stakeholders tell us that is the most expected technology combination. But it would be, of course, it would be possible, but then you need additional infrastructure and also as I've shown, the renewable electricity demand would be much higher for these hydrogen fueled sections.
So there's one last question. Well, for everybody that wants to know if we're going to have access to the presentation, the question is yes, I will be sending the links. And the actual webinar is recorded, so it's going to be uploaded on our YouTube channel of the chair, and so everybody can go and rewatch it as much as they want. So the last question is, with electrification of HDVs in Germany, how do you address resiliency of the transportation system? And was that cost incorporated in the analysis?
I'm not sure if I understood the question. Could you repeat it, please?
With electrification of HDV in Germany, how do you address resiliency of the transportation system? And was that cost incorporated in the analysis?
No, this cost was not included in the analysis, but and actually. Yeah, I mean it's a new field. It was not in the cost analysis, but we have done several studies on this and and think that within the next years we will have an electrification of smaller trucks until 12 tons due to the European CO2 standards. Because these vehicles are included, and these vehicles we learned from the buses. These vehicles are very resilient and have already high uptimes and good experience with these vehicles.
Okay, great. So that concludes our webinar. Thank you, both of you, for your excellent presentations. If anyone has additional question, I guess they can contact you. Your contact info are available in the PowerPoints. And on that, I thank everyone and have a good day.
Thank you, everyone.
Thank you.